Test 2. You got your test 2 back? Rewarded for coming to class, I guess. I'll post the grades, so if you're online, I'll post them right after class, and I'll post the solutions. As I was saying earlier, I just finished marking right before class. I gotta get them back. Gotta get them done, I guess. I will say that I'm so proud of you guys. You did so well. Usually test 2 is just not that great. And if you're feeling like, hey, that what's she talking about? That it wasn't that great. That's okay. You got redemption round for the final exam. So don't worry, you'll get to do it all over again on the final exam. So grab your test and make sure you use it to study, right? And here we go. All right, test 2 done. Next up, final exam. We got a little new topic, which is called regression. Okay, so chapter 8 is our last kind of topic that we're doing. And I was looking at the schedule here. I only have 8.1, but I think we can get into 8.2 today, which might kind of be nice to kind of get into it a little bit. So don't be surprised if we get into 8.2 today. Okay. And I think I can close that. Okay. And as I mentioned, these are all the assignments that are left, which means there's really only 2 real ones and 2 bonus ones. And you're all done, which is crazy. Okay. All right. So like I said, I'll post the solutions to the test. I just didn't get a chance to do it before class, but I'll do it afterwards. So you can see what I was expecting. All right. New chapter. I love ending on this chapter because although a lot of people kind of get used to doing hypothesis testing and confidence intervals, but they're a lot of work, right? And there's a lot of concepts, but once you get used to doing them, then they're pretty fun. And everyone's like, well, fun maybe not the word, but right, once you kind of get the hang of it, then it's good. But now we're going to change to something completely different. Don't worry, you can do hypothesis testing and confidence intervals in this section, but we tend to avoid it. I'll introduce it if we have time. So chapter 8 is generally called regression. And so specifically what we mean is linear regression. And so linear means what? It means a straight line. And regression is a line of best fit. And so really what we're building is lines of best fit. And so we're going to be talking about line fitting, residuals, and correlation just to get some concepts going, right? But in general, if you have a relationship, just as a quick review, what's on your y-axis is your response variable. That's the variable that you're interested in. And then you've collected some explanatory variables, which go on your x-axis. And then let's say you've got your data and it looks nice and beautiful like that. Right? Now, you could say, okay, well, I could model this relationship with a straight line. Right? And so really linear regression is, or regression in general, is often called modeling, right? Especially if you're in business, they love to throw the term modeling around. Oh, yeah, I ran a model. I just modeled this, modeled that. And really, all they're doing most of the time is fitting a line of best fit, right? And so it sounds cool, right? But, and that's important, right? But it's really just a line of best fit. It might help to remember what the equation of a line is. You might remember something like y equals mx plus b, an equation of a line, right? And so here, this is the equation of a line, which is going to come into play, right? Because I have a straight line and I'm modeling and building a line of best fit. Yeah. Which means we're going to find the slope and the intercept of this line of best fit. Okay, nice. Anything else? Well, I could talk all day about this stuff, but I won't. I could, probably. All right. I feel like there was something else I wanted to say here. Oh, yeah, I remember. We use regression, or in general modeling, right, or lines of best fit. The main use of them is, yes, we're modeling, but why are we modeling, right? It's to make predictions, right? And so we can use this line to predict values, right? Unseen values. And so we use regression or modeling to predict the response variable, right? That's the thing that we're interested in. So the general kind of flow is going to be, okay, you're interested in a response variable and you collect some other variables, right? The explanatory variables going way back to chapter 1. And you collect data, right? And then you make a scatter plot of that data, right? And now we're trying to model this overall behavior, right? You know exactly what the data looks like, but you also know at this point, hey, where's my pointer? Hello? It's gone. You can see I'm doing it. Uh-oh. To take my word for it. Oh, dang. Usually that works. Hands off. It's like it's completely frozen. Do I dare close this? Watch me. Okay. Oh my gosh. It's my worst nightmare. I can scroll, but I can't do anything. In my settings. What? Like, forget. Oh boy. Oh, my pencil is not connected. Feels risky. But I'm willing to risk the biscuit. Come on. Why doesn't it want to do it? Now I've done it, haven't I? Just a bunch of OC stuff popping up. I know, mine's got the, it should just do it. There, connected. Connected. Okay. Oh, phew. Thank you. Slide 1. It's kaput. I really can't remember. Oh, I do remember what I was saying because it's kind of important. So this is the sample that you've collected, right? And just like for inference, right? So hypothesis testing, confidence intervals, we understand that if you collected a completely new sample, right? Random sample, it's still a good sample, it'll be different, right? But you would expect the overall behavior to be the same or similar, right? And so that's what we're doing when we're modeling, right? And so that's why we use it, or that's how we can use it to predict response variables. So we're going to quantify the relationship between two numerical variables, right? Meaning X and Y are both numerical variables, as well as if you have a numerical response variable, we can talk about a numerical or a categorical explanatory variable. So really the only restriction is, and maybe I shouldn't highlight this, I'll do it on here instead. And our Y is the response. Now, for these methods to work, right, your response variable has to be numerical. Oops. Has to be a numerical variable. It is possible to model categorical variables, or the easiest one is a binary variable, right? A yes, no, 0, 1 situation. And so here the response variable has to be numerical, and we're going to start, because it's most common that the explanatory variable is numerical, but I also want you to see what it looks like if it's categorical and how that would behave. I suspect we won't get to the categorical until Tuesday, but I just want you to see it. And so here, for a categorical response variable, we use what's called logistic regression. So it exists, and it's even in your textbook. We just never get that far. And so we use logistic regression, which is kind of cool. But for this course, so this is not in this course. And if you like this stuff, there's a whole course on it, Stat 310. Wow, a whole course on lines of best fit. I know. It's true. It's a little bit more than that, but it's a lot more than that, but still. At its heart, it's lines of best fit. All right. So the example, every term I get here and I think, man, this is such a boring example and I should really change it up. But then I'm busy marking and it's kind of a busy time for me too. Not just, it's definitely busy for you guys, but it is busy for me too. And so I never think to change it. But I always say I will. Well, one day I'll change it. Anyways, we'll use it. It doesn't matter. The scatter plot shows the relationship between the percentage of high school graduates, or the high school graduate rate in all 50 US states and DC, and the percent of residents who live below the poverty line, which this is quite old, but it was defined as income below $23,050 for a family of 4 in 2012. So some percentage of each state lives below the poverty line, of course. And so we can talk about the percentage in poverty for a state and the percentage of high school graduates. And so first things first, right? If I give you a scatter plot like this, especially if I give you the y and the x-axis, then I expect you to be able to tell me what's the response variable. The response variable here is the percentage in poverty because it's on the y-axis. Right? What's the explanatory variable? Well, it's the percentage of high school grads because it's on the x-axis. And yes, I will, it seems simple, but I will start off that way on the final exam. All right? Give you a scatter plot, tell me what the explanatory variable, what the response variable is. I also want you to be able to describe the relationship. And in order to fully describe a relationship, you have to talk about 3 things. Just like how if we had a histogram, we had to talk about the shape, the center, and the spread, right? We still have to talk about 3 things, but we want to talk about, let's see here. We want to talk about linear versus nonlinear. So I just lump them into linear or nonlinear. So linear means just a straight line, right? Can you look at this thing and imagine a straight line doing a decent job of modeling it? Okay. What I will say is we're going to be quite generous. But when I look at this and I kind of squint a little bit, I feel like I can fit most of this data, and there's some wiggle room here, right? But I can fit this in this straight line relationship. And so that's why I'm going to go ahead and call it linear. Also, because in this course, we don't learn any methods for modeling nonlinear data. So you better tell me it's linear, otherwise everything we do doesn't make sense. So it's kind of a catch-22, I guess. So for the methods that we learn, has to be linear. I also want you to talk about if it's positive or negative. Now, in general, where can I put this? I'll put it up here. How about if I have a positive relationship, it looks like this. And if you imagine a little arrow on the right-hand side, then it's going up, which is positive, right? And for a negative relationship, then it's going to look something like this, right? And so again, if you put a little arrow on the right-hand side, right, then it's going down, and that's how you'll remember what the negative relationship looks like. Knowing that we're going to fit a line And the line has a slope and an intercept, right? Which you might not be terribly, or it might have been a while since you worked with y equals mx plus b, right? But if you have a positive relationship, then you're going to have a positive slope. If you have a negative relationship, you're going to have a negative slope. Right? We'll get there. So in this case, looks to me like the line's going down this way, and so I'm going to go ahead and say that it's negative. The last piece is the strength. And this, sorry, is the direction. The strength, you'll see all kinds of filler words, or what are they? What are they called? Descriptors. Moderately strong, right? I am fine with you just saying it's either weak or it's strong. Okay? And sometimes, you might feel inclined to say something like moderately strong or something like that. But your only two options that you need to worry about is weak versus strong. If you find yourself kind of second guessing yourself, if you can see a pattern, it's strong. Okay? And so if you can see a pattern, it is a strong relationship, right? And that's where you might, with practice, start throwing in words like moderately strong or something like that. But on the final exam, if you just tell me it's strong or weak, right? But it can only be weak if there's no pattern, right? And so if you can see a pattern, it's a strong relationship. So strong or moderately strong in this case. Because I was able to kind of squint and see some sort of pattern in here. Well, nice. Any questions about that? Where we're going to start is we're given the line of best fit. And I want to just establish some terminology and just some key skills. And then we're going to actually calculate the line of best fit. But we'll learn some stuff before then. So the linear model for predicting poverty from high school graduation rate. Now, the key is we'll always be predicting y. Yeah? And so what we're going to have in general is, and I'm going to need a little bit more room, I guess, y hat is equal to, usually we have b0 plus b1 times x. Y hat, now we've seen hats before, right? P hat is the sample proportion, okay? But this hat is different. Context will tell you it's completely different, right? Y hat versus P hat. Y hat is the predicted value of y. Remember, the whole goal of this exercise is to be able to predict values. And so the predicted value of y is your y hat. And that's the goal. Now, if you think about y equals mx plus b, right, m is attached to the x, and so whatever is attached to the x is the slope. And so here, we'll start there. And I'll clarify that the slope is attached to the x. And b naught, right, b subscript 0, is the y-intercept. We'll have values just like in this example here. And sometimes it's nice if we replace y, our generic y, with the name of the variable, right? Because how would you read this? This is the predicted percentage in poverty, right? Poverty hat. Our y-intercept is 64.78, and our slope is negative 0.62. And of course, the percentage of high school grads is our x. So sometimes we replace the x and the y just for to make it easier to read the regression equation. And so here, the hat, we use it to signify that it's an estimate or a prediction. So now what you can do is you can put in any percentage of high school grads, right, and predict the percentage in poverty for a state. Right? For example, the high school graduate rate in Georgia is 85.1%. What poverty level does the model predict for this state? And so we have the, and I'm going to add it here, the poverty hat is 64.78 minus 0.62 times the percentage of high school grads in Georgia. Notice that we use the 85.1, okay, as opposed to the 0.851, which I've drilled into you now, right? You get your percentages are proportions, and for math, we use the decimals, right? And so now it's kind of weird to see that we're keeping it as 85.1. But if you're ever unsure for regression, what I want you to do is check the scatter plot, right? And whatever the scale of the scatter plot is, that's the scale that you're going to use. And so here, this is in percent, and so we keep it as percents. And same thing here on the y-axis. It's going to result in a percentage. So the predicted percentage, predicted percent in poverty for Georgia is 12.018%. Now, the thing is, Georgia is one of the 50 states, and so it's in this data set, and we have some observed percentage in poverty, right? And that's the tool that we use to assess how well our line fits our data. Okay? And so that brings us to the residuals. Think about the word residuals It means leftovers, right? And so the residuals are the leftovers from the model fit. So you could rephrase it as the data is the fit. And this here, this red line is the fit. And the residual are the green lines. And the blue dots are the data. And so we've got our actual observations, right? Those are the blue dots. And then we have our line of best fit. And our residuals are the distances between the observed values and the line of best fit. Or the residuals spell today, is the distance between each observed value and the line of best fit at that value of x. And the line of best fit at the same value of x. So at 85.1, I suspect Georgia might be one of these, right? One of these first ones close to 85, right? And so we predicted a 12% percentage in poverty. Maybe it's a little bit over, I don't know. But then we have the observed value. And the difference between them is going to be the residual. So the residual is the difference between the observed value of y and the predicted value of y at the same value of x, right? So at each same value of x. This is on your formula sheet, if you can believe it. Look at us go. So close to finishing the formula sheet. We did this on test 2. Now there's a lot that's just here for completeness. We haven't gotten here yet, so we can kind of parking lot that for a little bit. We have seen this already, but we'll reintroduce it and we'll calculate the slope and the intercept, just like I was kind of foreshadowing. But here, what we're talking about right now is the residuals, the very, very last thing on the formula sheet. That's got to feel good. So on your formula sheet, I'm nice and I don't use the notation. I write it out in words and say the residual is the observed y minus the predicted y. Usually what we do is we use a lowercase e for the residuals. That's because it's also called the error. It's the error between the line and the data. It's also because R was taken. And so we'll see R later, the correlation. Which makes me think C was taken for the correlation. It's kind of a daisy chain. So yi is the observed value of y, and yi hat is the predicted value of y. But like I said, you've got this nicer version on your formula sheet, but it's saying the same thing. So what does that mean? It means in your data set, every observation is going to have a residual. Okay? And so this means every observation will have a residual. We can calculate those residuals. The percentage living in poverty in DC is 5.44% more than predicted, right? So here, this is the observed value for DC, and it's quite a bit higher than the predicted value of y at that same value of x, right? They have to line up. Okay. And so then we get a positive residual versus the percentage living in poverty in Rhode Island is 4.16% less than predicted. Right? And so we can have our observed value of percentage in poverty and our predicted value, and a negative difference would put you below the line. Okay? Now, what's kind of mind-boggling if you think about it, or don't think about it, I guess, is the mechanism that is used in the background that we're completely ignoring, okay, that fits this line. Okay? What it does is it goes through and it iterates, and it minimizes the residuals. Okay? Not just the residuals, but the residuals squared. Okay? And so what it's doing is it's finding the line of best fit is taking into account all these residuals, and what makes it the line of best fit is that all the residuals are as small as they can possibly be. Okay? And so that's how the line is made. And I know what you're thinking, well, how can you make a line based off of the residuals if the residuals are the distance from the observed values in the lines? Well, that's why there's a whole course on it. So, not for us, right? And what's really nice is if you have a scatter plot, it's really easy to get Excel to just plop the line of best fit on there, right? And so, saving you a ton of work, right? And so we just need to be able to interpret it. What does it mean? So, you've probably heard the term correlation before, right? And so correlation is a way of, well, it's the way it describes, it's not usually how we talk about it, right? If you say, oh, there's a correlation between those two things, just ignore this for a little bit. What does it mean, right? Kind of intuitively, if you're saying, oh, there's a correlation there, right? It means that they move together, right? And so if one of them changes, then you expect the other one to change as well, right? And so correlation technically describes the strength. I'm going to take it one step further, not just describes, but is a numerical measure, really busting out the big guns here, is a numerical measure of, sneak that in here, of the strength and direction of a linear relationship. we've seen this before though, right? Where, okay, the mean is really only a good measure of center if you have a normal distribution, for example, right? But we can always calculate the mean, right? And so that's where our knowledge about stats comes into play. Same thing, you'll always be able to calculate the correlation, right? But it's only useful if you have a linear relationship. Right? And so it's a numerical measure of the strength and the direction of a linear relationship. Now, as a fact, it takes on values between -1, okay, so that's a perfect negative relationship, and +1, which would be a perfect positive relationship. And in the middle, a correlation of 0 indicates that there's no linear association, right? There's no relationship there. In terms of, I like to do a number line, kind of like this, between -1 and 1. I'll throw 0 in the mix. Now, correlation is denoted by a lowercase r. I use a lowercase r. The textbook uses a capital R. So if you're reading the textbook, don't be thrown off. The lowercase and the capital R are the same. R. So if you have a correlation of -1, what that looks like in terms of your scatter plot is a negative relationship that are on a perfect line. If you're on the positive side, so the correlation is 1, then you're going to have a perfect positive relationship. And to illustrate that they don't have to be so steep, I'll do this one kind of shallower. That's okay, as long as they're on the same line. 0 is a little bit harder to draw, but it's just going to be a cloud. And no pattern. And so here, if R is 0, there's no pattern. Now, what's going to happen as you move out, of course, you might have already guessed it, and that's great. If your correlation is positive, then of course you'll have a positive relationship. Versus if it's a negative value, easy enough, you have a negative relationship. Otherwise, they behave the same. I'm going to give you, just because it's nice to have kind of a threshold of, okay, well, we know that a relationship can be either weak or it can be strong, right? And so roughly around -0.5 and roughly around 0.5, I'll just give you that as a general guideline. Okay. All of this I would consider weak. And remember, a weak pattern is one where you don't really see a relationship, right? You can't see a pattern. After that, we can start saying that, all right, here, this would be a strong positive relationship, so 0.5 up to 1, roughly, all right? And Same thing here. If I go between negative 0.5 and negative 0.1, then I have a strong negative relationship. Roughly 0.5. Yeah? So if you can see a pattern, then the correlation will likely be about 0.5 or higher. Right? And if I had to guess, a correlation of 0.5 might look something like that. You have to squint a little bit, right? But I can kind of tell myself I can see a pattern there. Huh? Or if it's negative, maybe let's do it at kind of 0.7, negative 0.75. Might look something like this. A little bit stronger. Okay. Good. So the correlation, nice, right? Because it tells us about our relationship, not just if it's positive or negative, but also the strength of the relationship, right? And just remember, correlation has to be between -1 and 1. So for our scatter plot, which of the following is the best guess for the correlation between the percentage in poverty and the percentage of high school grads? All right. Process of elimination, I think, is the way to go here. We already decided we have a negative relationship, right? Which means that I can exclude any positive correlations. There's another one that we can eliminate right away, knowing that the correlation has to be between 0 and 1. It can't be negative 1.5 because it's a baddie. Which means I really only have two choices here, right? So I'm choosing between negative 0.75 and negative 0.1. And going back up here, right, negative 0.75, okay, looks good-ish. I mean, I made this up, so. But I also know that, okay, anything around 0, I really wouldn't be able to see a pattern, right? And the fact that I'm able to see a pattern here tells me that my best guess in this case out of these options would be negative 0.75. Let's see. We did it. This scatter plot has the percentage in poverty, so the same response variable, but of course there are other explanatory variables, and I think this one is just kind of hilarious. They collected the percentage of female householder no husband present. I don't know. They thought, oh, let's collect that too, I guess. Whatever. We're just here for the scatter plot. So, looking at this relationship, now you kind of have to squint a little bit and be a little bit lenient, right? But I'm seeing kind of roughly here. Notice that I'm not always including all the points, right? It's okay to exclude some outliers, right? If you think in general, right? We're talking broad strokes, right? What's the pattern? So here I feel like I could describe this with a positive relationship, which means my correlation should be positive, which by the same process of elimination means that I can eliminate two of those, right? The negative ones. Now, I'm choosing between 0.1, 0.9, and 0.5. 0.1, well, I already saw a pattern, and so I really don't feel comfortable with 0.1. And by the same logic, but on the opposite end, right, I don't feel comfortable with 0.9 because I really had to kind of squint here, right? 0.9, they would be all really, really close to the line, right? Or pretty close to the line. And so kind of by the same reasoning, this is what a correlation of 0.5 would look like. And let me just remove these so you can just see what it would look like. Right? If you make a scatter plot, you see this, this is what 0.5 would look like. Right? And so that's why, in terms of my threshold that I'm letting you use, or encourage you to use, right? Anything smaller than 0.5, right, is not going to have much of a pattern at all, right? And so, because it's kind of hard to see a pattern here, we had to really talk ourselves into it, right? And so that's what it would look like. Right? And then it's going to tighten up as you get closer to 1. Oh, nice. Maybe I'll draw those back on. Good. Which of the following has the strongest, I'll ditch one of those, has the strongest correlation, that is a correlation coefficient closest to +1 or -1. And so you're allowed to move in either direction. They're both strong. Okay? All right. A is a decoy because, why? It's a decoy because this is a nonlinear relationship. It's a really, really strong linear relationship. It's nonlinear relationship. Critical mistake I made, right? And so this is a really, really strong nonlinear relationship. But what the correlation does is it fits the line, which might look something like this. And then it figures out how many values, or kind of how far are values from this line. Once you've done that, this correlation would be quite small, right? And that's because it only works for lines, right? And so it is strong, but it doesn't have a high correlation. And so now we're just choosing between B, C, and D. And I'm going to go for B because it looks like it has the tightest relationship. All right. And so here, right, this would be the strongest linear relationship. So it would have the highest or the strongest correlation. This would be the strongest positive correlation, and D would be the strongest negative correlation among those three, right? And then C is garbage. But any questions about that one? Or the previous ones? I knew it. Nope, 7, no, 8. Good thing I didn't just plan on doing 8.1. Well, I did, but then here we go. I felt like we could get it to 8.2. It's good. It'll give us more time to review next week. Last week of classes. Can you believe it? Yeah, we can. We can believe it. Fitting a line by least squares regression. So when we talk about regression, usually we are talking about least squares regression line, but we drop the least squares. But we'll talk about why it's least squares in just a couple of slides. So how do we create that line? So we had one goal, right? We want a line that has small residuals or minimized residuals. Yeah? And we already talked about how do you calculate those residuals. And so really we want a line that kind of captures most of the activity. So there's a couple of different options, right? And we've seen these options before when we were calculating the standard deviation, right? So if you want to minimize the sum of the magnitudes of the residuals, right? Why do you have to minimize the magnitudes, so the absolute values? Is because if you have some values that are below the line and some that are above the line, they will add to 0. Yeah? And so we need positive values because as a fact, the sum of the residuals just on their own will be 0 because of how we fit the line. Because of how we fit the line. So adding them up isn't going to help because they'll just cancel each other out. So we can take the absolute values to make them positive, but the option that we use and that is most commonly used in almost every industry is we want to minimize the sum of the squared residuals, the least squares. And so that's the same conclusion that we got to for the standard deviation, right? We have the squared deviations, and that's how we find the standard deviation. And so why least squares? Well, it's the most commonly used. That should tell you. It's easier to compute both by hand and by software. And most of the time, a residual twice as large is usually more than twice as bad, right? And so if you think about a square, x squared is a parabola, right? And so if you go from a residual of 1 to a residual of 2, right, then if y is x squared, here y is 1. Oops, I'll do it. Whereas if you've only increased by 1 unit, right, all of a sudden you're being penalized for that because it's more than twice as bad because it puts you at y equals 2 squared, which is 4. Right? So that's what that means. You don't have to worry about that, but that's the logic behind it. All you need to know is that this is the method that we're using. And so the least squares regression line. The least squares regression line, right? If we think about, well, we're seeing some Greek letters, some betas in there. Uh-oh. That means there's a population equivalent. Of course there is, right? And so what we've learned throughout the course, right, is that we collect a sample, right? and we're able to calculate things from the sample. We can calculate the slope, we can calculate the intercept, but really what we're interested in is the population model, right? And so what we're trying to learn about is the population intercept and the population slope. And so we'll still have a predicted value of y, and really these are your parameters, right? Your beta naught and your beta 1, and then your x. Don't worry, we're not going to, well, it's tempting. Okay, I'm not going to commit to it, but I will say, if you have a hypothesis about what the slope is, right? Usually we start at, hey, is the slope equal to 0? Right? The population slope equal to 0. A slope of 0 looks like this, right? Means that there's no relationship there. You can plug in any value of x and you would get, just keep getting the same value of y. So it's kind of useless. Right? It's not until you get a non-zero slope that you're starting to get information. And so we could, I'll emphasize the could, we could test the null hypothesis that beta 1 is equal to 0. Right? Is the population slope equal to 0, or is the population slope something else, something of interest, something happening? Right? Emphasize that we could. But usually we're a little bit tired by that point, so we skip it. But you could, and you know how. In fact, what's really fun is the test statistic is just a t, right? And so it gives you a t, and you know how t behaves, okay? And, right, regression output includes the test statistic. Hey, maybe we will do it, which is a t and the p-value. That's nice. Oh. So if you're using Excel, which you will, right, then it'll give you the test statistic, your t and your p-value, and it'll test if the slope is 0. Usually we don't care about the intercept, right? The intercept is just where it crosses the y-axis. And so a line keeps going forever and ever and ever. And so at some point it will cross the y-axis. And usually that's not that important to us. All right, that's enough theory. Well, it's all theory, I guess. But if we have a parameter, beta naught, I should clarify, this is a beta. Hopefully you've seen a beta before. It's a little cute bee with a tail, the beta. The point estimate is that b subscript 0 or b naught that we had in our model, right? Y hat equals b naught plus b1 times x. So the slope is, the population slope is beta 1, which means our point estimate is our b1, b1 times x. So when we build models, we calculate b naught and b1 based off of our sample. So using our sample information, we can calculate B0 and B1. Before we can do that, let's talk about the conditions. So the conditions for fitting a line of best fit are, well, the first one's kind of obvious. It has to look like a line, right? So linearity is the first condition. And so this must look like a straight line. To be modeled by a straight line. I always feel like that one should be pretty obvious. Nearly normal residuals. What would that look like? So your residuals are the distances from the line to the observed values. Now, in order to be nearly normal, in fact, centered on 0 is what they should be. Which means that roughly half of the observed values should be below the line, right? And roughly half of them should be above the line. Right? There's a little bit of wiggle room because sometimes they compensate, right? But most of them should be really close to the line, and there's some wiggle room, right? You're allowed to move out a little bit, but not very many of them. Right? So, as we said, in your data set, each observation will have a residual, right? You can calculate the residual, the observed minus the predicted. And so then once you have a column of residuals, then you can make a histogram of them, right? And just make sure that it looks approximately normal. The last condition is the constant variability. Now, what that means is you have to have even spread around the line, right? Or roughly even spread around the line of best fit. So as an example, if you have something like this, then that's roughly even spread around the line. Versus if you have something that looks like, and maybe I'll make this one a little bit bigger so you can see it better. Let's see if I can pull this off here. So nice and tight, and then all of a sudden, there. Can't resist. The line of best fit here would likely look like this. Right? These tight values are really going to determine where the line goes for the rest of the values of x's, right? But the problem is that we have kind of between here and here-ish, right? We have good predictions, or good, and by good, I mean slash reliable predictions. Right? But only for that little stretch of x's, right? Whereas here, right? Because if I use this line, so if I plug in a value of x and I use the line to make a prediction, then it's going to be a pretty good prediction, right? A reliable prediction. I feel like I kind of crossed the line there. I'll move some of those out. But then what happens? As my x's increase, right, and I start to use this line of best fit, then if I map this up, so if I use this value of x in my predicted value, I would get a predicted value here, but it could go as low as down here, or there's a huge stretch of potential values, observed values. The problem is our line of best fit has no way of taking this kind of shape into account, right? And so that's why you have to have constant variability in order for your line to be reliable. That said, you can still fit a line. You would just have to add a footnote saying your estimates might be unreliable because you have non-constant variability. And that's not a good look, is it? Here's my prediction. I don't feel very good about it because it happened to be in these kind of bad values of x. That's not good. So here we have unreliable predictions. So in terms of the linearity, like I said, I think the linearity condition is pretty obvious, right? Like I said, unless it fits like a, or looks like a straight line, that's the only way that you can fit a straight line to it, right? Or should. Of course, methods for fitting a model to nonlinear relationships, they exist, right? But are beyond the scope of this class. And so there's lots of extra resources, right? But you can do it. We're not going to do it. Although I will point out that one common trick, if you have a nonlinear relationship, is to transform the data. And depending on what the shape is, a common transformation that you could try is you could try the natural log of x or the natural log of y. So one common trick if you have a nonlinear relationship is to transform the data. For example, you could try the log of y. If you remember logs, again, beyond the scope of this course, but the neat part is once you've done a transformation, the reason you're transforming it is to make it look like a straight line. And there's lots and lots of scenarios, especially in biology, where you have these exponential growth relationships, then taking the log, which would kind of undo it, straightens it out, and then you can fit a straight line to it. And so is to transform the data, then fit a linear model. Which is why we spend time working with linear models here, because usually you're able to kind of force a linear model, even if that's not where you're starting. Right? So it's kind of cool. So either way, you use a linear model. One thing that you can use that we don't really use that much anymore, but you can have a scatter plot, right? And so here, these are the original scatter plots. It's more if you're fitting a ton of different models, then you assess the fit of each model and you pick the best one, right? And so one of the ways that you can do that is by a residual plot. Now, a residual plot is going to look very similar, right? Except it's got your residual plot is going to have the residuals. I need more room. On the y-axis. And then there's some different methods, but then you have your explanatory variable on your x-axis. And there's usually a line, and that line is usually at 0. The reason we use the residual plot is because it magnifies the relationship in the original scatter plot. So residual plots are used to magnify relationships in the original scatter plot. So if it's hard to see in the original scatter plot, usually it'll be a little bit easier to see if there's any problems with linearity or constant variance, right? Or now I can't remember what the last or the middle one was. Normal residuals, right? And I want to just add a page here. I've been doing pretty good. I haven't been adding pages till now. So for a residual plot like this, so here, if we have a residual plot, that means you have your residuals on the y-axis and you have your explanatory variable on the x-axis. In terms of linearity, the linearity condition, the linearity condition is going to be satisfied if you have just random scatter around 0, right? And so I'll say even random scatter around 0. This is only in your residual plot. The normal residuals, right? The normally distributed residuals is also usually satisfied by even random scatter around 0. Right? Or you could have tighter scatter around 0 and then less as you move out. Right? And so it would be not necessarily even, but random scatter around 0. Most around 0 with fewer as you move out. Fewer points further from 0. I'll say that. And then the constant variability. Again, you would want even random scatter around 0. Right? And so it's just a way of being able to quickly check all those conditions. So even random scatter around 0. So from the original scatter plot, this looks like all the conditions are satisfied, and the residual plot doesn't give me any issues, right? Whereas here, if we only looked at the original scatter plot, then you might be able to talk yourself into a linear relationship. And I will say most of the time, you're still going to fit a straight line to this, right? But you'd make a note saying, okay, there's some non-constant variability or non-linearity here that we're ignoring, but it is magnified in the residual plot, right? And so that's all it's doing. Here, again, I don't know if this one magnifies it that much, but it's supposed to show that we've got this kind of funnel shape, which is the non-constant variability. And here I'll say nonlinear. Of course. So residual plots, might seen them, you might have seen them. Hey, I forgot this was here. Maybe I didn't need a whole plot or a whole page. So residual plot, right? It just kind of takes the line, straightens it out, and puts the residuals on the y-axis instead. But this is the original graph, and this is the residual plot. We've already talked about these, so I'll just kind of zip through them. So I've got a goal in mind, but we'll see. So the residuals should be nearly normal. Okay? And so you can make a histogram or a normal probability plot. Probably called it a QQ plot, but I'm not even sure we've talked about them. That's okay. Doesn't matter. It's just a way of checking if it's normal. Or because you guys are so good at hypothesis tests, there's a hypothesis test that you can run to check to see if it follows a normal distribution. So the null hypothesis would be it follows a normal distribution, right? And the alternative is that it doesn't. Right? And in that case, you're hoping to not reject H naught, right? And so it kind of depends on what your goal is. But it's all out there. It exists. Can't remember the name of it right now. It doesn't matter. It exists. That's cool. So constant variability. I will, so here we already talked about it, but I will also point out that it's called homoskedasticity. It's kind of hard to say. Homo's the same, right? Homoskedasticity. And so variability, skedasticity. But I only point that out in case it's on an assignment. I can't remember if the term comes up on an assignment or not. So, but it's not something I expect you to know beyond that. Well, what condition is this linear model obviously violating? Well, it doesn't look like a linear relationship to me. I'm gonna lock that in. Wow. it's obviously violating the constant variability, right? The homoscedasticity. This is where I wanted to get to. Nice. So it's pretty old school, but the reason I keep it on the final exam is because it's easy marks and it's kind of just calculations anyways. And so I'm doing it for you guys. What we're going to do is we're going to calculate the slope and the intercept, right? And so we will calculate the slope and intercept of a line of best fit. So on your formula sheet, and maybe I'll add a page here. Oops. Hey. Just fumbling over here. There. And so it is something that I will get you to do. And like I said, the only reason I'm keeping it is because it tends to be easy marks on the final exam. And that's my goal for you. Still have to work at it. Still. Oh, it jumped me. Jump around. Crazy. There. And maybe what I should say, slope and intercept of a, instead of using the kind of common term of a least squares regression line would be the technical term. On the final exam, it'll say calculate the slope and then calculate the intercept of the least squares regression line. So let's have a look at what's on your formula sheet, right? So the least squares regression line, just as a reminder, is the y hat plus b0, b naught, plus b1x. Okay? And I even tell you that the slope is b1. Okay? And how we are going to have to calculate these is you first calculate the slope and then you calculate the intercept. And you'll see why when we look at the equation of the intercept. But first, calculate the slope. So that's why it's listed first. The slope is b1. Now, r, we know is the correlation. Right? So r is the correlation. The correlation is that numerical measure of the strength and direction of a linear relationship, right? And so that's how our slope is going to be either positive or negative, right? And so that's where that comes from. S subscript y is the standard deviation of the y's. And we've seen that before, right? But it's the standard deviation of y, which means, of course, S subscript x is the standard deviation of x. So far, that's 3 things that I need to give you. right, in order for you to calculate these. Once you have the slope, then you can calculate the intercept. But notice the reason we need the slope is because it shows up here. Now, of course, whatever you find for your slope on the final exam, I'll follow through as long as what you found is what you use to find the y-intercept. Okay. A common mistake that I see is mixing up your x's and y's. Right? And so, right, 1 over 2 is very different from 2 over 1, for example. Right? So it's going to make a huge difference on your slope. But then whatever you find for your slope, you're going to use it here to solve for your y-intercept, which is here. Then find the y-intercept. Y bar is the mean of y. You need the average of your y's. And x bar is the mean of x. You think about your scatter plot, right? You've got your y variable on your y-axis and your x variable on your x-axis. So I would need to give you all these 5 things. So for a regression question, I give you these 5 things. We'll level up just a little bit. There's a couple of different ways that we could get the correlation, and so we'll talk about that. But for now, just those 5 things, I have to give them to you. All right. Then once you have your slope and your intercept, right, your y-intercept, then you can put them back in, and then you have your regression equation like we did at the very, very beginning of today, right, where it just said, hey, this is what it is. So what would that look like? The simplest form, well, that's nice, is going to look something like this. I guess I should keep the graph. First thing you're going to do if I give you a scatter plot, right, is just make sure you've got your y and your x labeled, right? Because even if you didn't have this and I didn't give you the labels, right, which is perfectly reasonable, then you would need to map this information to an x bar, y bar, sx, sy, right? The percentage of high school grads is your x, so that's how you would know that that's your x column, right? And you're given the mean and the standard deviation of both your x and then your y, but the percentage in poverty is on the y-axis, and so of course those values would be for y. The mean of x is x bar, and the mean of y is y bar, right? And so it's your job to map these generic values, right, to the values that I give you. Right? Usually I don't give them to you this nicely. The standard deviation of x is sx, and the standard deviation of y is sy. But I will give you those. And finally, the correlation, which is a numerical measure of the strength and direction of this relationship, right? Negative 0.75 is what we're told. And so we'll do kind of a fake part A. Find the slope of the least squares regression line. Now, from your formula sheet, right, you have to find the slope. B1 is R times SY over SX. All right, let's start there. Spare a line. So this is where it's really important that you've mapped your SX and your SY to the right variables. All right. The correlation, B1 is R is negative 0.75. SY is 3.1 and SX is 3.73. Now, because they're so similar, those standard deviations, it's not going to make a huge difference if you swap them, but it will in the long run, right? But numerically, it won't. 3.1 divided by 3.73. In terms of math compared to the math that you have been doing, it's not too bad, I think. B1 is roughly negative 0.6233243968. You're allowed to do some rounding here. In fact, I'm going to scroll ahead and see. She usually only keeps like 2 decimal places. So I'm going to do the same. She did. Do I know Mina or what? I wish I knew Mina. She's the author of the textbook and these slides. She's so cool. B1 is negative 0.62 to 2 decimal places. Save ourselves some trouble, right? Because now, what do you think part B is going to be? Find the y-intercept of the least squares regression line. I'm just going to copy that. From the formula sheet, oops. Be careful you don't swap your x's and y's, right? It's going to be B naught is y bar minus B1 times x bar. Yeah. So here we go. Y bar minus B1 times x bar. Order of operations, and this is where people kind of trip up, is you have to do the multiplication first before you subtract from the y bar, right? So just be really careful about that. But your y-intercept is y bar. Again, important that you've mapped your numbers to the right variable, right? Take some time to do it properly. 11.35 is my y bar. Minus my B1, which is negative 0.62, times x bar, which is 86.01. You have to do this multiplication first, right? And then subtract it, right? You'll be subtracting a negative, and so that makes addition, right? But you can, if you use brackets, your calculator should do it for you. So 11.35 minus negative 0.62 times 86.01, negative 53.3262. I can't bring myself to round quite yet. I'll round my final answer. So now 11.35 minus that guy, 64.6762, or let's do to 2 decimal places to match, just to keep it nice and simple. All right, B0 would be 64.68 to 2 decimal places. Nice. All right. Then what? Usually, the next part that I give you or ask you is construct the least squares regression line. Or equation if you prefer. Well, the least squares regression line or equation from your formula sheet, it's on here, right? The least squares regression line is this. Okay? So all I'm really asking you to do is take your y-intercept and your slope that you found and put them into the equation of a line. Okay? So y hat is b naught plus b1x. But now I have values for b naught and b1. So y hat is 64.68. I'll start with the plus, but the slope is negative 0.62 times x. So simplified, y hat is 64.68 minus 0.62 times x. Notice that you keep your x and your y hat open, right? Because the whole goal is to be able to plug in any value of x that you want and find the predicted value of y, right? And so they're just, well, variables, but they're just placeholders. Right? All right. I think that's a good place for us, and we'll pick up here on Tuesday next week. If you have any questions, let me know. And if you didn't grab your test yet, please do. I don't want them. I'll see you. Enjoy your weekend. See you on Tuesday.